Let's discuss the symmetric group algebra. Let's suppose we have a finite group G and that we consider the group elements with coefficients in C. So if we consider these linear combinations, we get the group algebra. Alternatively, we can consider the coefficients, for instance, in Z or Q. We will consider the group G to be the symmetric group. That is the permutations of a finite set of n elements. For instance, when we consider S3, the permutation group of 3 elements, it contains the identity, the exchange of 1 and 2, of 1 and 3, of 2 and 3, a cyclic permutation, and the other cyclic permutation. And the group algebra has dimension 6. The group algebra has a center, and the center is generated by elements which are sums over the elements of a conjugacy class. So you consider C of lambda, where lambda is a conjugacy class, and we consider the sum of all elements in the conjugacy class. This gives us an element of the group algebra, which is clearly in the center, because if we conjugate C, we just get an equivalent sum over elements of the conjugacy class. Let's consider these sums for the 3 conjugacy classes of S3. So for our example, we have the identity conjugacy class. Then we have the transpositions, which consists of 1, 2 plus 1, 3 plus 2, 3, as well as the conjugacy class of triplets, 3 cycles, which is 1, 2, 3 plus 1, 3, 2. In this example, let's explicitly compute the structure constants of the algebra, which is the center of the group algebra. So we make a table with CE, C2, and C3, and we're going to multiply them. And then the table of multiplication is that CE is the identity element. And so we can easily fill out the first row and first column. The next entry is given by C2 times C2. So we can obviously get 3 times the identity element. And we have already 3 elements, but we should in total have 9. And since the only class that can appear is the conjugacy class of the 3 cycle, we must have 3 cycle conjugacy classes as well. Then when we multiply a 2 cycle by a 3 cycle, we can only get 2 cycles. So we'll get twice the transposition conjugacy class. And then when we multiply a 3 cycle with a 3 cycle, we can get twice the identity element plus once the 3 cycle conjugacy class. So this is the table of multiplication, and these are the structure constants. A more complicated example is if we consider Sn with n generic, and we multiply a 3 cycle conjugacy class with the 3 cycle conjugacy class, then we get twice the double 3 cycle conjugacy class. We get 5 times the conjugacy class of a single 5 cycle, 8 times the conjugacy class of two cycles. Then we get 3n minus 8 times the 3 cycle conjugacy class, and n times n minus 1 times n minus 2 divided by 3 times the identity conjugacy class. So this is a non-trivial calculation. So for instance, the first coefficient 2 one gets by realizing that, for instance, 1, 2, 3, and 4, 5, 6 for n bigger or equal than 6 is duplicated by taking 4, 5, 6 in the first sum over 3 cycles and 1, 2, 3 in the second sum over 3 cycles. So we get each double 3 cycle twice. The last coefficient, for instance, is gotten by realizing that we must pick 3 out of n elements, which gives us n times n minus 1 times n minus 2 over 3 as the possible permutations that give rise to the identity element. But again, we can take 1, 2, 3 in the first, and then 1, 3, 2, which is its inverse in the second, or we can take 1, 3, 2 in the first and 1, 2, 3 in the second, and then both of them give rise to the same identity element. So we have to do this, we have to do this number, which has a 1 over 6 in the denominator. We have to do it by 2 times 2, which gives this coefficient. Similarly, one can compute with a little more effort all the other structure constants in this expression. There are a few questions that one can ask about this expression, which have been studied by mathematicians, like how general can we make a calculation of this structure constant? What is the most general class of explicit structure constants that we can compute? And what is the nature of these polynomials in the variable n that appear as structure constants? These questions have led to very interesting answers. However, there are most likely classes of structure constants which have interesting combinatorial interpretations and which have not yet been computed.